So how about the deprotonated form? What would be a logical name for the deprotonated form? We know that in general, the deprotonated forms are called carboxylates. But how would we name this particular deprotonated form? Well, the key is that we use an ate suffix. So instead of calling this ethanoic acid, this would be called ethanoate.
Okay.
It might be sodium ethanoate or potassium ethanoate, whatever the counter ion is, but the anion is called ethanoate. Notice how we add the ate. Or if we were going to use the common name, it would be called acetate. There's a slight difference there because there's no O anymore, but the general theme is that the deprotonated carboxylic acids are named like the protonated forms except with an ate or an O8 suffix. Oh. Remember that one of the ways to indicate quantitatively how acidic a compound is with the Ka. This is something you might remember from general chemistry. Now, I don't know, do you remember, if something is acidic, does that mean it has a big Ka or a small Ka? For example, this is the most acidic compound in the exercise we just did. Well, if something is very acidic, does that mean that its Ka is big or small? Do you remember that?
It's small, isn't it?
Turns out that the Ka is big.
Okay.
Basic explanation for that is, remember that Ka is just the equilibrium constant for the deprotonation reaction. The Ka is just an equilibrium constant. Well, here's the general form for an acid that's going to lose its proton. If something is very acidic, does that mean that this equilibrium lies forward or reverse? If this is very acidic, does that mean we're mainly going to have the starting material or the product?
We're going to have mainly the product.
That's right. That indicates a big Ka. When a reaction's equilibrium lies far forward, the Ka is big, because this is just the equilibrium constant. A large Ka means that you're going to end up producing lots of products. So something very acidic is going to have the equilibrium far forward here, so it'll have a big Ka. Confusingly, though, there's one problem with Kas is that they tend to be very small. Like, I don't know, 10 to the -5, or 10 to the -6, or 10 to the -11. So an alternative way of measuring the acidity is the pKa. The pKa can be much more convenient because if the Ka is this inconvenient number 10 to the -6, then the pKa would just be 6. It's just the negative of the exponent. The pKa is just the negative of the exponent, which gives us a more convenient number. Well, anyway, this is what I think you were thinking about earlier. When something is very acidic, it has a small pKa. That's probably what you were thinking when you said that the Ka should be small. It's actually the pKa that should be small. And so this is something that's not very acidic. So would its pKa be big or small? It would be big. So it's important to have both of these in your notes so we don't get them confused. The reason there's an inverse relationship between these is because the pKa is the negative of the exponent, while taking the negative inverts the relationship. Your instructor talked quite a bit about pKa's in the lecture notes, so it's good to know that something very acidic means a small pKa. That would be a big Ka. Here's another problem where we can try to figure out who is the stronger acid. We want to try to figure out who is the stronger acid in this pair. First thing that will probably help is writing out the structures. So let's start by writing out the structural formula for this compound. Good. And I think I'll give you some help with the structure of the other one.
All right.
We got the methyl group, and we have the S, and now we need to figure out how we can arrange 3 oxygens around this sulfur. That's something we could figure out by going back to drawing Lewis structures, but it might take us a while. How are we going to arrange these 3 oxygens? It turns out that they arrange like this.
It's similar to the sulfuric acid that we've been using.
That's a good point.
I mean,
Yeah.
as far as the
It is similar to sulfuric acid.
of a methyl group.
Yeah, absolutely. That's a good point. So these are what are called sulfonic acids as opposed to sulfuric acids. But that's a good point. The structure is similar to what we've learned about the structure for sulfuric acid. So this is sulfonic acid. But you're right, it has a similar structure. Well, maybe it's best just to memorize this so we don't have to figure that out. Well, now we need to figure out which of these is the stronger acid.
The sulfonic acid is going to be stronger.
I think that's right. And what would be your explanation for that?
Because, well, it has 2 pi bonds.
Mm-hmm.
So you're going to have at least one resonance form that's going to be able to stabilize the negative charge after it's been deprotonated. The oxygen's been deprotonated.
Okay.
And it's also, well, it's also fairly electronegative too.
Who's electronegative?
The sulfur.
Okay, that's a good point.
More so than the carbon.
That's an interesting point. Okay, good. Those are good points.
And then you also have a little bit of maybe of an, I don't think the methyl group would matter much in the whole scheme of that molecule as far as balancing.
Especially because they both have methyl groups. So, but even so, yeah, whether something's a methyl or a ethyl or hydrogen is not as important as whether it's a sulfur or a carbon or the resonance. Okay, those are good explanations. Let's actually draw what these would look like after they lose a proton. So these are the deprotonated forms. Now, you mentioned a bunch of good points in your explanation. The one that we want to focus on particularly, though, is resonance. Usually, resonance is stronger than other effects. Resonance tends to be stronger than other effects if there's competition. So let's focus on resonance. Now, this negative charge is stabilized by resonance. How many legal resonance structures are there for this molecule?
There's one more than what we have there, so two resonance.
That's right, or at least there's 2 major ones. There's probably some other minor ones we can draw, but they're, let's see. So I think you said 1 in addition to this, which would make 2 total. That's right. Or another way to put it is, how many places are there that we can put this negative charge? 2, including where we have it right now. There's another resonance structure where we can put the negative charge on this oxygen. Now, in total, how many major resonance structures would there be, do you think, for this molecule? How many places in total can we put this negative charge?
There's 3 places on each of the oxygens.
That's right. That was the one part of your explanation that wasn't quite clear ahead of time. You mentioned before that there was at least one other resonance structure, but if we can put the negative charge up here, we could just as well put it down here. We can put the negative charge up here. But we could just as well put the negative charge on this oxygen. All of those are just as good as the others. So that would be the most important stabilizing effect here, the 3 resonance structures, as opposed to only the 2 over here. I think the point that you mentioned, though, that this sulfur is more stabilized than this carbon is a good one. I think sulfur is more electronegative than carbon, so that would also tend to stabilize the negative charge. And there's even an extra thing that you didn't mention, which is that these oxygens also stabilize the negative charge by induction, because they're electronegative too. But this negative charge here is only stabilized by this one oxygen by induction, whereas this is stabilized by the two oxygens by induction. But the most important thing to emphasize here is the resonance.